In this video, we're going to look at the case where our dopant atom comes from group 3 of the periodic table. In this case, we call it an acceptor impurity. And so, as I mentioned in a previous video, a common example of this is boron. And so, of course, being in group 3 is going to have 3 valence electrons compared to silicon's 4 valence electrons. And so again, let's keep in mind that this process of doping that we're talking about is substitutional impurities. So substitutional impurities, and so what that means is we can consider our silicon lattice the same as we did when we were introducing a phosphorus, except now we're just going to replace it with a boron. So let's say again we want to change the same silicon atom. So we can come in here, we can get rid of that Si, but we also need to get rid of 4 of these electrons that belonged with that silicon atom. And so now let's say we want to introduce a boron here. So because boron only has 3 valence electrons, it can bond with 3 of the 4 nearest neighbors, but it can't bond with the 4th one. So we essentially have this open spot here. And so what can happen then is, like we talked about in our previous video, there's of course still this thermal process of electron-hole combination going on throughout the crystal. So let's say, for instance, maybe this electron up here has enough thermal energy to break away from this bond. So if that happens, this electron is going to go away. And so let's say this electron is moving from here, and so it can actually come down and fill in this open spot here. Of course, when it does that, it's going to leave behind a hole. So we have this positively charged hole that was left behind. Let's make that positive sign a little cleaner. So down here we have, let me label this, this is our electron that came down here, and it's come into this spot where our boron was. So our end result is we have this positively charged hole which can move around, and we have this boron which now has attracted this, let's see, let me get a good color so we're not conflicting here. Let's do yellow. So our boron, so if we look at sort of this boron area here, we notice that it's going to have a net negative charge. And so let's sort of write down some of these observations. So in general, our boron has an open spot where it can accept a free electron. So open spot to accept a free electron, which is coming from the conduction band. So of course that's where our terminology comes from in terms of calling this an acceptor impurity, because it's accepting free electrons from the lattice. So as I mentioned, once it does accept an electron, that boron becomes ionized. So we have an ionized boron atom, and so the charge is negative. So ionized boron atom, which just like our ionized phosphorus, is going to be fixed in the lattice and cannot move. And so ultimately what that means is that we have this hole which can move about, but there's no corresponding electron because that electron has been captured by that boron. So we've created a hole which is mobile. So we have a mobile hole with no corresponding electron. So this goes back to a couple videos where we were talking about doping, and we said we can create only holes or only electrons. Well, this is how we would do it. So again, keep in mind though, we still have this electron-hole pair process going on in other places in the lattice. So again, maybe we have this electron down here has enough energy to break away. So let's say that electron is breaking away and it can come somewhere else in our lattice, let's say over here, and that leaves behind a hole. But if we dope this to the appropriate level, and I'll talk about what that is in the next video, our boron and the associated holes that come with our boron are what's going to be dominating. And so let's talk about some terminology then. So if we're using acceptor impurities such as boron, so acceptor impurities, then we call our holes the majority carriers. So actually let me write holes are majority carriers. And so same sort of reason as we had in the previous video with electrons. In this case, there are just more holes than there are electrons. So for that reason, our holes are called our majority carriers. And something I didn't mention explicitly in our previous video is that this means that our electrons are then called our minority carriers because there are fewer of them. So same thing in our previous video, we could have said that our electrons were our majority carriers and our holes were our minority carriers for that case. So one other sort of piece of terminology here is because these holes are positively charged, so we're talking about our holes are positively charged, so that's a P, so we're going to call semiconductor doped with acceptor impurities p-type. So whenever we're talking about acceptor, we know that we're talking about p-type semiconductor. And so the reason I say that is because for several devices later on, we're going to talk about various combinations and various configurations of p-type, n-type, and so this way we can sort of track back to our basics if we need to.